Hello, and in this statistics video we're going to have a look at principal components analysis. That's a technique for reducing a large number of measured variables into a more manageable set of components that can still explain a large proportion of the variance in those measured variables. So it's basically a way to simplify a measure without losing much data in terms of what you can find out about the people who have been measured. I want to say before we start this, as I do in all my statistics videos, is that I'm a second year undergraduate student just getting to grips with statistics. So this is intended to be a simple introduction and sort of guide to interpretation and example, and more importantly how to do it in art. There are other great videos explaining principal components analysis in art, and they go into a lot more detail than this video will, but this is intended to give an easy introduction pragmatically to someone who's just starting out. So with that said, let's dive in. I've got an art console open here, and I've got some data frame data frame called D. So if we run that, this is the example data we're going to be using. We've got 25 observations on 10 variables, and basically the fictitious idea in this study is that notebook manufacturers wanted to create a scale to find out what's most important, what they should prioritise when they're making a laptop. So everyone rated from 1 to 10 how important these each of these variables are to them when they choose a notebook. So we've got solidity, colour, mass width, style, power, speed, storage, OS, and resolution. Now some of these terms seem to be related, and it seems a little redundant to have 10 questions when you could have a simpler measure that would still be good and that more people probably fill out because it's simpler. So we want to see if we can find the underlying components that these variables are measured in that represent these variables that might get at the construct a little more easily. So that's what principal components analysis is for. But before we start this, there are a couple of things we need to check and a couple of packages we need to load. If you recall from my previous video, a package is some add-on functionality that you can get for art. So we need a package called Psych, which you can get from install packages Psych. Among other things, that's going to give us everything we need for the actual principal components analysis itself. In addition to that, I also want to load a package called GPA rotation. Now this is for orthogonal rotation, which is something we'll talk about a lot when we do the actual analysis. So install.packages GPA rotation. If we submit that command, both packages should go ahead and install, and that happens successfully. So we're now ready to do the analysis. The first thing we need to do is, for some of the assumptions we need to check. We need to get a correlation between all of the variables. So to do that, I'm just going to put it in variable R, and I'm just going to say that equals the correlation of all the variables in the data data frame. Actually, I called it D, and then we want to show that our variable. So here are the correlations between every variable with every other variable, and this is the first thing we want to check when we do a principal components analysis. You want to check that none of these correlations are either too high or too low, because if you think about it, if they're too high, then they're probably measuring exactly the same thing, not just different parts of the same component, but they're probably measuring exactly the same thing. And if they're too low, then they're out on their own. They're not measuring any aspect of even the underlying component we want to look at. So if we look at these correlations, generally they're okay. There are a few red flags like this one. For style with speed, there's only correlation negative 0.18. So there are some issues there, but I generally think this is okay for what we need to do. This is simulated data, so obviously I know what the outcome is, and I made this so that it's pretty clear cut what the two components are. But in a real world, you might want to look at this more carefully. The next thing we need to check on is what's called Bartlett's test of sphericity. If you know from repeated measures and over, Bartlett's test of sphericity is basically saying that it checks whether the correlation matrix is proportional to an identity matrix, and put simply, a matrix just means a collection of numbers. If it wasn't for these labels here, this would be a matrix if there were no labels. So it basically, Bartlett's test of sphericity checks this matrix and tells us if any of the these off-diagonal correlations are the same, because if all the correlations are the same, then it's obviously not measuring underlying factors, and there's no point in continuing with the analysis. So we want to run Bartlett's test of sphericity, and to do that we're going to do core test .Bartlett, and then we want to give it our correlation matrix right, so that's called R, and we also need to tell it the sample size. So in our case, I just happen to know that we asked 25 people to fill in this fictitious questionnaire, so I'm going to run that, and we see it gives us chi-square value, and this scientific notation is minus, so behind 0, so it's much less than the cutoff of 0.05 that we use for significance tests. So we can say this is a significant Bartlett's test, and what that means in this context is that we don't have sphericity, which is a good thing. Normally when you do multi test of sphericity in repeated measures and over, you want the matrix to be spherical, because you need that for the test, but in this case we need it to be rejected, so that's good. There are a couple more things we need to check. One is the determinant, which we can get from doing DET, and this we have to call on the raw data, so I do a DETD. So we have to call it on the correlation matrix, and this is going to give us one number. Now, this is what I meant about it being a simple analysis. I don't really know what this means. It's to do with the issue of how. It's all to do with the issue of how variables relate, and a heuristic that's often talked about is this should be more than 0.001, and obviously it's not in this case. It's 0.0004. So this assumption isn't really met, but say this is example data, so we're just gonna kind of forge ahead as if it had been. You also want to check whether your variables are normally distributed, which in this case I'm not going to go into, because it's pretty simple. If you did want to do that, one way you could do it is by the Shapiro-Wilks test, which you just run Shapiro.test and then put in the name of the variable, but say I'm not going to do that in this case. In terms of assumptions, the last thing we want to test is the KMO. This is a test of sampling adequacy, and basically the idea behind it is that because we're trying to find underlying factors, we need a lot of data. We need a big sample size. So this takes into account the correlations, how easy it is to find out the underlying factors, takes into account the sample size, and gives you a value which you can suggest compare to a criterion value. So in this case we're going to run KMO, and we want to give it our matrix, and we really want to look at the overall value here, and we've got 0.79. Now, Kaiser 1974 wrote that values of 0.5 are barely acceptable, and 0.7 is just getting into the range of being good. The higher you go up the scale, the more adequate your sample size is. So some of these individual these individual values are encouraging as well. So we're going to assume that's all our assumptions checked, even though some of them aren't true of this data. But we're gonna assume that that's the case and forge ahead. So we now need to do our actual principal components analysis. Now, the procedure is to run a base analysis that has the same number of components as there are variables. That will then work out for each of the components how much variance that component explains, and then we need to run a second model, and based on the first model we can make a judgment about how, like, when the additional components stop explaining variance, so how many components we do actually need to extract. So let's go ahead and do that. So I'm just going to do base equals principal and I'm going to give it the raw data frame because of calculation of factor scores, which is something we'll talk about later. And I'm going to say rotate equals none. Now, rotation is something we'll definitely talk about later, and it's very important to make the interpretation of what the factors are more important. But for the base model, we don't want any rotation, and then we need to specify how many factors we want to extract. This is or component. Sorry, this is why we need a base model, because first of all we need to extract a component for every question, and then just decide based on that what we're going to reduce it down to. So I'm going to say there's 10 questions in this case, so we're going to say n factors equals 10. Now there are several. I'll just run that to show you what the output looks like. There are several ways we can decide how many factors we want to extract. The two that I'm going to talk about are called the Scree Plot and the Eigenvalues. Now, if you're going to use Eigenvalues, there are some things that have to hold true, and you just sort of compare it to an absolute value. It's been recommended that if you have more than 250 participants, you can look at a visual representation, and if you have less than that, you can look at the eigenvalues. I would look at both, as we're going to in this case, but before we look at the eigenvalues, there's something to check, and that's the commonalities. That's the amount of common variance shared between each of the variables with other variables on the factor. So to get an idea of what the commonalities are, we can run our base model and ask for commonalities. And here are our initial commonalities for each factor. Now that's because when you first do the analysis and you have the same number of components as you do variables, then obviously each factor is gonna share 100% of its variance with that variable. So that's fine. If we want to look at the eigenvalues to decide how many factors we're keeping, we can just say our model name and then values. Now that's going to give us eigenvalues for each one of our components. The heuristic that people use is that if this is above 1, you should keep that component. So fortunately they're ordered in size. So we've got first eigenvalue of 5, so that shows we definitely need to keep the first factor. Second eigenvalue of 2, which shows we need to keep that factor. And this third one is where using an absolute criterion gets a bit misty, because this is 0.93, which really substantively is quite close to 1. So using an arbitrary cutoff like that isn't always the best, but we certainly have converging evidence to what I theoretically intended when I simulated this data. Obviously you wouldn't have this if you collected real data, but I intended for there to be 2 components extracted. So you can see, even if we forget about the absolute value, if we look at the relative magnitude of these values, these 2 are a lot bigger than the ones that precede it. So we're going to keep 2 factors. Another way you can look at this is to plot them in what's called a Scree Plot, and like I said, if you have above 250 participants, this can be very, very useful. So we want to plot something from our base, and we want to plot these values. That's going to give us a window like this, and this is called a Scree Plot. This is basically the amount of variance explained by each factor plotted against the factor number, which is here is labelled as index. So we can see that after the second factor, the third factor explains much less variance. The usual practice here is to say if you do a line against this graph, where it would get to right angles, you keep everything that's to the left of that. So the eigenvalues go down a lot. So the second or third factor, like we saw, even just looking at the raw values, the third factor is kind of there, but the heuristic is usually get everything to the right of that. So that's the first and second factor up here, and say that converges with other evidence. But when you're looking at it, it might not be that clear cut. So you just kind of have to make a judgment about your data about that. But that's what statistics is about, really. So we've decided we're going to extract 2 factors. So to do that, we want to run another principal component analysis, but this time we're going to call it our model. And this time we've decided we want 2 factors, so I'm going to replace that with 2. We also want some rotation. Now, when these factors are represented in geometric space, what we want to do is make it so that what one variable is really close to one factor, and the other variables that are part of the other factor are really close to that one. Because if all the variables loaded onto both factors the same, then and the loading is about the correlation between the variable and the factor. If the loadings were the same, then we wouldn't be in any better position than we were before we did the analysis, because it would be really difficult to interpret. So there are 2 types of rotation. There's orthogonal rotation and oblique rotation. Now, orthogonality is about right angles, so it's gonna make sure that the 2 factors are at right angles, and that the individual factors are allowed hardly any correlation between each other, so they're going to be really separate. The second type is oblique rotation, and that does allow factors to correlate. Some authors have said that in psychology, or orthogonal rotation should never be used, because theoretically it's unreasonable to expect that psychological constructs don't correlate, because we know they do. So once you've decided between oblique or orthogonal rotation, you've then got to decide which specific rotation you want to use. The default, as you can see down here, is very max, which is why I had to specifically specify none. The 2 that I would recommend are very max and direct oblement, which are both implemented in our very max is an orthogonal rotation, and direct oblement is an oblique rotation. So I'm going to specify oblement because I want to do an oblique rotation. If we submit that, and now we look at our model. We can see we've got several factors. So these are what's called loadings. Tells you how much one variable loads onto each factor, how much it contributes or correlates with that factor. So this is what we use to interpret. So we look at the context of what the variables are supposed to be measuring, and look at the relationship to determine what factors represent. So it seems like the first group of factors have very weak relationship with component 1, and then the second group of variables have a strong relationship with component 1. So that would suggest that again there's 2 factors, and if we look at the variables that load strongly onto component 1, for example, they're these variables. So we need to look at what differentiates power, speed, storage, OS, and resolution from the other variables in such that they represent a different dimension. Well, if you kind of look and interpret this, the first factor, solidity, colour, mass, width, and style, kind of have to do with the form of the laptop, and the second group have to do with the function of the laptop. So when you're looking at these, you just have to kind of interpret them and make a call as to what what you're going to call the factors. So, two more important things to look at here are the proportionate variance explained. So the first factor explains just marginally more the variance in the data than the second factor, but altogether they explain a lot of the variance. These are percentages. So the next thing we get down here is the correlations between the components. So they have correlation of -0.4. So that there is some correlation between both components. That they are related somehow, but it's pretty weak. If you did orthogonal rotation, you probably wouldn't be looking at this so much. We then have a chi-square test, which basically tells us how good this model is, and then a measure of fit. I believe this is the same as R square. So it's basically going to tell us how much proportional variance we've explained with both those components. Both explain at full 100% of the variance. So that's good. Heuristically, the criteria for being a good model is that this value needs to be above 0.95. So we've kind of met that assumption here. So that's the basics of a principal component analysis, really. There are a couple more things you might want to look at, like biplots, see how the factors and variables are represented in a geometric space, but really you don't really need that to make an interpretation, basic interpretation of what's going on with the factors. Another thing you might want to look at, though, is, or use in some future analysis, is the scores. So we're going to say model scores, and as you can see, there are 25 scores here, and there were 25 participants. So what this gives us is how each participant would have scored on this underlying dimension. So how important form is to them, and how important function is to them. So once you've done a principal component analysis, you can use those underlying dimensions in future analyses. So that's the basics of principal component analysis. Really, it really was the basics. There's a lot more to it than that, but there are other great videos you can watch for that. But yeah, guys, thank you for watching this video, and I hope you learned something. Bye bye.